Yeah, so I will talk about transparent data visualization. And of course, since I'm speaking for the first time for this audience, I wanted to learn a little bit about Uruguay because I basically didn't know anything. So to remind you, we are here in the Northern Hemisphere. It's summer over here. I work at the University of Amsterdam and you are located approximately there. And what was funny to find out is actually that your country is about 5 times bigger than ours, but you have also 5 times less people. So it should be really spacious. And what was also funny to find out is that our highest peak is actually 350 meters, which is not that high. But I also found out that Uruguay is really flat. So your highest peak is around 500 meters. So I think the country should look pretty similar in that respect. And we also owe a lot to you guys because one of your best strikers, I guess, played for Ajax for a while. So Luis Suarez, we are very happy to see him play because he made a lot of goals for Ajax, which is, of course, the favorite team in Amsterdam. So thanks to Uruguay for that. Okay, so let's go to the science now. I think you already did a great job introducing me. I'm a chemist actually from training, and we develop a lot of the genetically encoded fluorescent probes. We try to employ them for cell biology and try to learn more about the inner workings of cells. So we spend a lot of time behind microscopes and gathering data. And of course, we want to then reproduce or show and visualize the data in the most optimal manner. And so today I will speak about 2 things. I think I will mainly focus on the colorblind friendly figures. And they connect actually quite naturally to the web apps that we use for data visualization because there are colorblind friendly color palettes in those web apps. So that goes a bit hand in hand. So when we speak about color, I want to remind you that color is actually an electromagnetic wave, and there's a whole range of electromagnetic waves with different wavelengths. So that can vary several orders of magnitude. We have quite invasive electromagnetic waves. So they represent, for instance, X-rays, and very non-invasive electromagnetic waves that we use for communication, for instance. And there is a very, very narrow band in between, somewhere in this range. And those electromagnetic waves can actually perceive with our eyes. And then that is, that depending on the wavelength, it is perceived as a certain color. So we have this narrow bandwidth between 400 and around 700 nanometers that we can perceive with our eyes. And depending on the wavelength, that electromagnetic wave evokes some activation in our eye that gives rise then to the perception of color. And colors are, of course, very important in human vision. But there are, depending on who you are, varying levels of how good you are at perceiving colors. And there's this deficiency, it's called color blindness in normal language. But it's maybe more accurate to call it a color vision deficiency. And that's because only very few people are really completely colorblind and can only see black and white. That's really uncommon. So although it's normally called color blindness, it's not accurate. It's okay with me to call it color blindness, but some people are more sensitive to the language and think it's the wrong term. So actually color blindness is the inability to distinguish certain shades of color. And red-green color blindness is the most common form, and it's inherited. And I'll also explain a little bit how it works. It's quite interesting also from a scientific standpoint. And it affects mainly males. So around 1 in 12 males is colorblind and only 1 in 200 females. There's no treatment available, although there are certain companies that sell glasses with the idea that it can kind of solve the problem of color blindness. I've tried those glasses because I'm colorblind, but for me, they didn't really work. But maybe they work for other people. I'm not really sure. But there's no treatment available. So the way colors are perceived by our eyes is with three types of cells, cones in your retina, and they are either sensitive to short wavelengths, middle wavelengths, or long wavelengths. And in case of the most common green and red color blindness, either this medium wavelength cone or the long wavelength cone is affected or completely destroyed. Depends a bit on the type of color blindness. So a blue color blindness it also hardly occurs. And then you have these kind of simulations. So you see here a nice painting or a traffic light in full color. And then it's simulated here to demonstrate what a colorblind person would see. So for instance, if you are red colorblind, this red cone is not present and then the painting would look like this. And in case of green color blindness, the painting would look like that. I have no way of telling if there's a big difference because I'm colorblind. So to me, this painting actually looks quite similar to that one and this one slightly different. But I think for people with full color vision, these two paintings look different than the original. And I like this one very, very much as well, this picture. It's a kind of color vision test, but it also directly with the text gives you the type of color blindness. So, for instance, I can read this line, your green vision is correct, but there is supposed to be a line up here that I cannot read at all. And it says here, for me, it says you are red blind, which means I'm red color blind. So this is a very quick and easy test to see if you are colorblind. And there are other tests as well that you can do, or you can also find them online. Yeah, and this is a scheme of how this color blindness is inherited. So this is a kind of a family tree that I made because I'm also in this family tree. I'm this pronounced black box. I'm male, so I have an X and a Y chromosome. And the gene that is responsible for color vision is actually located on this X chromosome. And all the blue X chromosomes are affected or mutated chromosomes. And if we now move up in this family tree, here are my grandfather and grandmother. So both my grandfathers were colorblind. But in this case, these are the grandfather and grandmother of my father, so the guy with the XY chromosome, but they both, so my grandmother here passed on the X chromosome, my grandfather the Y chromosome, so this is not really important. But on the other side, so the parents of my mother, the mother was just wild type, and my grandfather was, you could call him the mutant, and he passed on the X chromosome to my mother, and she is now only a carrier because this mutant X chromosome is compensated for. But now when my parents got children, and incidentally, I have only brothers, so only males here. My father, per definition, passes on the Y chromosome, and then there's a 50% chance that the wrong X chromosome or the mutated X chromosome is passed on. And again, coincidentally, it was passed on to all their sons. So all my brothers are also colorblind. Yeah, there's a fourth brother here, but he was adopted, so that's not really a family. He's a good control, but it's and then what is interesting actually that what you can see here, I have this mutated X chromosome, but I got two boys, and then I passed on the Y chromosome and not this mutated X chromosome. So in this case, the mutated X chromosome is kind of excluded from the gene pool. And on the other hand, I have another brother. He got two daughters, and he passed on this wrong X chromosome. So his daughters now are carriers, and when they get boys, then they may get colorblind boys. And what you can see in this family tree now is that it usually skips a generation. So it goes from these males, then you have a female carrier, and then you have these colorblind males again. So that's an interesting feature of colorblindness. All right. Yeah, then just some personal examples of color use that works very poorly for me, just to give you an idea. So this is a dashboard that was used by our educational services. And I can quite nicely see this red color. And only later I found out that there are two green colors. So I just recorded them as green, but there seems to be an orange as well. But to me, those are basically the same colors. So I cannot distinguish between them. So I also gave them that feedback that they probably need to use different colors to make it more accessible. And another example is, and that's, I think, because I'm red colorblind, people also often use red text to highlight something because it really stands out for people with good color vision. But to me, this red text, it's almost, it's very close to black. So to me, it doesn't really stand out. And also only later I found out that all these wiggly lines are also red. I thought they were just black. So it's much better to use, for instance, a color that's a bit lighter, like these two examples. That works much better for me. All right, now let's turn to the use of color in, for instance, scientific figures. There is different uses of color. So we talk about qualitative color scales and quantitative color scales. In case of the quantitative color scales, the color usually represents a number. I will give some examples of that. And in case of the qualitative color scales, the colors are more used as a category or a label. And I'll first give an example of this, of the qualitative color scales. So some examples of colorblind color scales are these two. So they're made by Okabe, Ito, and by Toll. And they were especially made as colorblind friendly color schemes. So I use these quite often. And especially this Okabe Ito is becoming more and more popular. And it's also the one that I really like. So that works very well for me. And this is just an example of where this color scale is used. It also showcases one of the web apps that I generated. In this case, it's the Superplots web app, in which, for instance, you can compare two conditions, a control and a drug condition. And instead of aggregating all the results, the biological replicates are colored in a different way to distinguish them. And their summary is highlighted with the bigger symbols. And now in this case, the replicas are labeled with different colors. And this Okabe and Ito color scheme was used. And that works really, really well. Here's another example. It's an example of line plots from an output of some time series. It shows 4 plots with increasing, how do you say, colorblind friendliness. I'll go through them one by one. So the upper left one has lines with different colors, but these colors are really difficult to tease apart. So when we apply this colorblind friendly palette, this Okabe and Ito palette again, the lines become easier to separate. But there is still a bit thin, so it's quite hard still for me to connect the line with the legend. And to make the lines more pronounced and more easier to identify, you can make them stronger, which really helps. So now it will become easier to connect them to the legend. And if you want to do this in an even more direct way, you can also use this direct labeling. So now the label is next to the plot. And this is actually the best way to display this kind of data. It's not quite common yet in science to do this direct labeling of lines. Usually people like to have legends, but actually I think it's the most easy way to identify or separate or label the lines. And of course, this only will work for limited amount of lines. So maybe up to 10. If it becomes more, then it will be horribly complicated. Okay, then some examples of quantitative color scales, and they are again can be grouped in 2 categories: sequential color schemes and diverging. And in case of in both cases, these colors then represent numbers, but in case of the diverging color scale, they have a midpoint which is usually 0. So that's quite often used for microarray data, for instance. So, and this is an example where they apply different color schemes to these kind of microarray data. So the classical way is to use green and red colors, but for green-red colorblind, this is of course impossible to see the difference. So there are some really nice alternatives. So I like this green magenta, for instance, and then black is basically the 0, the midpoint, but also this purple orange works very well. There is a cyan red alternative on the upper right, but since for me red and black are pretty close, this also doesn't work that well. And so this is an example of these kind of data where blue represents a drop or a negative value and red an increase. 0 is the midpoint. And this data visualization is actually excellent for me. So that works really well. So that's an example of a diverging color scale that's also colorblind friendly. And then some examples of sequential color scales, those you find, for instance, to make false color images of microscopy data. So they basically start from 0 and then you have increasing values. And this is a nice example. I think there is some kind of fluorescence image from some kind of pollen grains. Of course, the background represents 0 values and is black when you use the gray color scale, and then white represents higher values or higher intensities. And the classical way to false color represent this is, for instance, by jet or by rainbow color schemes. But the problem with those is that they don't use lighter colors for higher intensities. And then the color scheme is not what they call perceptually uniform. And this is now better in this case in the viridis color scheme. So they use colors ranging from blue to yellow. And what you also see, besides the use of color, they also use dark colors for the background for low values and lighter colors for higher values. And so you can also convert this easily to black and white. And if you would print this in black and white, it would also still be nicely visible. So this is becoming also more and more used to use this, for instance, this viridis color scheme for these kind of images. So those are called perceptually uniform. So they go from dark colors to light colors. And clearly this rainbow color scheme doesn't adhere to that rule. The other color schemes are pretty okay. And I think most common and most popular nowadays are these viridis and magma color schemes that we also use quite a lot. I'll give some examples also of this. So this, for example, some data representation of an experiment that we did in a heat map style. It's actually from calcium imaging. So here the colors represent calcium levels, and lighter colors are high calcium and lower colors are low calcium. Here you see time. So it just shows how the calcium changes occur over time. And this is now the viridis color scheme that was used here. But you can also use these color schemes to false color your grayscale microscopy data. So this is an example of a time lapse of defining cells. So it was a grayscale image, but we used here this magma color scheme to false color these kind of data. Okay, yeah, and then in microscopy, of course, you have a special case because we often have multi-channel data and then we want to make overlays. So to each channel, you assign a different color and you can make a nice color overlay. And usually when the structures are very well separated, like here, then it doesn't really matter what kind of colors you use. But when you start to mix them or look at co-localization, then it becomes more important to use colorblind friendly colors. So, for instance, if you want to show co-localization, the classical way there to do this was again use green and red, and then the overlay of the overlap becomes yellow. But again, this is not colorblind friendly. So I cannot tease out here the difference between yellow and green, for instance. So nowadays it's more common to use green and magenta, and then with the same data, you get these kind of images. So now you have either magenta colors or green colors, and where you have overlap, the structures become white, and this is now also colorblind friendly. Okay, so to summarize, I come up with some recommendations for the use of color. So yeah, it's easiest if you just use from the start colorblind friendly palettes. If you use them by default, for instance, this Okabe Ito for these kind of labels or lines or categories. And then for more quantitative data like microscopy images, you can use viridis or magma, for instance. And yeah, it's better to stay away from these kind of rainbow color scales. When you use thicker lines and larger symbols, it will also be easier for colorblind people to identify the color or to connect the data to a legend. And where possible, you can use patterns or different symbols or labels in addition to color. So then you have a bit of redundancy in the coding that also makes it easier, of course. And for the qualitative color schemes, like the Okabe Ito, you can only use a maximum of 8 different colors, because otherwise the colors will be harder to separate. Yeah, this is another recommendation. Use a legend that shows the color instead of using their names, because colorblind people have a difficult time connecting a color that they see with the right name, because yeah, it's hard to identify the correct color. And when you keep the legend close to the data, that helps, but also this direct labeling helps. And of course, it can help if you made a data visualization to consult someone who is colorblind and to test it. So you have these kind of simulators. For me, it's of course hard to judge how well they work. So for me, it's much easier, I think, to just consult a colorblind colleague. And of course, maybe I should mention that colorblindness is a heterogeneous disease, right? So, or it's not a disease, deficiency. So it may be different for different colorblind people, and even normal humans see colors in slightly different ways. So the way that people perceive color also differs between people. Okay, that kind of summarizes this part about color. Yeah, I have some further reading. I can share the slides afterwards, so you can find those hyperlinks more easily, and you can check this out if you like to. Then I'll want to say something about the web apps that we develop. I will talk a bit about the rationale. I don't have time to highlight them all, but I will just try to explain our motivation for developing them and where we are going with these kind of web apps. So I have a huge interest in data visualization and in making different data visualization, and also trying to find out what is the right way to visualize data. And if you want to learn more about data visualizations and the different ways that you can visualize data, these 2 books are highly recommended. So they're freely available on the web, and you can just browse through them. It's really nice. But I think they don't really show the tools that you can use to make the data visualization. So I want to say something about those tools that you could use. So how are you going to make a data visualization? So I would say there are basically 2 categories. There is point and click software that's very user friendly. So for instance, Excel or GraphPad. And they have some advantages, like they're very easy to use. They also have some downsides, like they are commercial and closed software. They're often not super flexible. It's hard to make reproducible data visualizations. And they usually don't have the most up-to-date data visualizations available. I say here they are outdated. Okay, that's a bit of a strong statement. It's not that bad. And on the other hand, you can also use open source software tools, but they often require you to code the data visualization, like R and Python, and it's becoming more and more common to use those. So those are free and open. They're very flexible, they're fully reproducible, and they allow modern data visualizations. But their biggest problem, I think, is that it's quite challenging because first you need to learn this coding language. And so with the web apps, we try to combine the best of two worlds. So we wanted to make tools that are free and open, kind of reproducible and easy to use. And so that's why we started to develop those web apps. And the web apps are actually based and written in R, but with a nice, friendly user interface. So the motivation for generating these apps was really to make life easy and to have with little effort, nice graphs that are state-of-the-art and publishable. There was also motivation to make this for our, for instance, for master students that do internships. They don't have the time at that moment to learn to write code. So for them, it would be really nice and easy if they could just upload their data, click a few buttons, make a nice data visualization that they then can show, for instance, in meetings, and that allow them to discuss their data. And at the same time, we also want to promote good practices like colorblind friendly palettes. So they're available, like showing all the data. So bar graphs are not really allowed in our apps. So we want to promote good practices with these apps. And then also transparent methods. So, and the code is open sourced and available, so you can really see what we are doing. And you can even take the code and extend or modify the apps if you would like that. Yeah, this is just an example of what we do with those web apps. We were interested in, yeah, these are called kinase translocation reporters. So they're biosensors, and this is just a fluorescence image of those biosensors that report on kinase activity. So the fluorescence is normally in the nucleus, but when the kinase is activated, it's pushed to the cytoplasm, and that can be analyzed in pretty high content. So that's what we actually did. So we tracked all those cells and visualized their responses over time. And so you see the output of this data in this graph, where the change in cytoplasmic to nuclear ratio was plotted as a kind of measure of the kinase activity over time. And this was done with the plot twist app to make this data visualization. And one nice aspect of that app is also that it allows easy annotation. So for instance, we can show with this bar where the stimulation took place. And one nice aspect that I really like, because fluorescence images are often on a black background slide, so it would be nice to switch quickly, for instance, to the dark mode. So with one click on a button, I mean, it's a minor thing, but you can also make these things with a dark background, which is nice for black slides. And yeah, it allows flexible data presentation. So also with one click of a button, we can change the data visualization from this line plot, for instance, to a heat map. So it's exactly the same data, but in a different way. And you can also sort these responses then in different ways. So yeah, this is just a very basic example of what we can do with those apps and how we, yeah, that it is highly flexible. So it will be hard to do this, for instance, in Excel in a very quick way. And of course, you can do this with code, but you need to write completely different code, whether you want to make this data visualization or that one. So all those tools are available at a single website at our Huygens server. So there you can access them. We have over 8 different web apps. And it may seem a bit of an overkill, but they're quite, how do you say, focused on one type of data visualization. So for instance, we have data visualization apps for static conditions, so comparing different conditions. And we have different web apps for instance, time series analysis. And more recently, we have this web app for superplots in which you can label the different replicas. And we have even a web app for reading data from 96 well plates, but this is an example of a very focused application. I mean, it's maybe an advantage, but also a disadvantage. So I'm still thinking about making one super app, but I didn't have time yet to do that. Yeah, now when we compare those point and click web apps with writing code, you can see that there are still some differences, of course. So one limitation I would say with the web apps is that they're not flexible, right? We upload them and you can use them, but you cannot tweak everything that you would like. So if you would like all the power that you have in your hands, then you really need to go to code, because then you can basically do everything. So I think also maybe people that find the web apps attractive, but still limiting, they should consider to learn some code, some R to further tweak it and take it further. And I'm actually working on a kind of protocols book that describes how you can make these data visualizations in R and ggplot as well. And I call them protocols also. So there are specific examples of how you can, for instance, make a data visualization for spectra or these kind of line plots. And it really takes you step by step through this data visualization. And also, I hope by providing this code, it will be easy for people that want to tweak it to modify it to their own needs. So you can check this out. It's still a work in progress. And if you miss a data visualization that you would like to see the protocol for, then please contact me. I'm very much interested in adding more protocols. Oh, and then maybe an example of where, another example of how you can use those web applications. And this is something that I've been doing more lately. So those web applications can also serve as a way to share your data. So especially if you have data from a proteomic screen or genomic screen, this may be very useful for other people as well. And instead of just dumping an Excel sheet somewhere in supplemental, you can also provide this as a web application where people can actually nicely access the data and play around with them a little bit. So this is an example of collaboration with someone that did a mass spec screen. I cannot really explain all the data, but we get different hits and candidate genes. And I'll just show you an animation of what you can do with this. So this is more of a dashboard now, right? So the user can browse through these different dots, get access to their data. You can filter it a little bit, tweak it a little bit, maybe zoom in, zoom out. You can highlight some candidates or find your own genes, maybe see where they are located. And this is now a much more accessible way to publish your data. Of course, it takes a bit of effort because you need to write a web app, but it also makes it much more accessible. So I'm not saying you should do this for every figure that you make, but if you have some useful data, this would be a way to publish it. So that brings me to the end of the talk. So the web apps are all gathered on one server. I'm writing some blogs, and then this book is very much a work in progress, but if you like, you can check it out. And if you ever want to discuss anything, you can contact me through email. I'm also available on Twitter, where you can contact me. And if you have any questions now, I'd be happy to answer them, but you can also contact me later if there's anything that you would like to discuss. And with that, I'd like to thank you for your attention.
Thank you very much, Joachim. Wonderful talk. Really, I appreciate a lot the talk that you have delivered for us. I think it's really an amazing area that you have developed, and we are all thankful that you not only develop for you, but you also put for service of the community. So it's free for everyone, and this is really remarkable from you. I want to make a point. So, well, we have now time for questions. So if everyone wanted to do a question in the chat, please paste it there. Meanwhile, I have several annotations that I want to talk to you and discuss with you. Starting from the end, I wasn't aware about this polar volcano plot. And it reminded me immediately to a kind of a plot that I was exploring around and taking advantage of these star plots, right? That you normalize whatever variable you have in a vector of 0 to 1, and then you can put this in different angles, right? And you can even play around in permuting and how they, fight each other. Is similar to this or something different?
Yeah, it's very similar to that actually. Okay. Yeah, I didn't try star plots, but it's quite easy to make. Okay. Yeah, so this polar volcano plot, it was the idea of someone else, and he asked me to make a web app for that, and I was pretty much intrigued because I didn't know at first how to achieve that. But yeah, it's a nice way to, how do you say, put multiple plots next to each other. So, and I think one of the issues with the star plot is indeed it's important to permutate them, because the sequence and how you rotate them can also kind of be, how do you say, can give different perception of the data.
Yeah, at the end of the end with the star plot, this permutation is also some sort of minimization. You find one which works better than others in trying to separate, different groups. But it's surprising, and I think it's a really wonderful tool. Absolutely. Then I have a couple of questions more in the use of the color scheme. For me, working with spectra and with also with the film and these techniques, when you want to show degrees of changes or many different components or something like that, the shed or of the rainbow is like the best option you immediately have on front. But of course we recognize this is a problem. Many people can lose some of the aspect that you are trying to publish just because we are not aware of this limitation as you mentioned in the vision. I find that the variety or this other continuous color scheme still lack of this diversity in color, right? Mm-hmm. And I wonder if you ever thought in use this OKB Ito, but in a degree of color between the different stack in order to generate a color scheme that can be a merge of 4 or 5 or the 8, whatever you need in order to have a color scheme continuous with more little, variance between one to another. Can be this.
Yeah, it's a good question. So I think.
And how you will perceive, you as a person who has a sensitivity of this, right?
Yeah. So I recognize this, right? Because the viridis color scheme maybe only goes from blue to yellow, so it's kind of. Yeah. I think what you see there is the. I say. This is probably the limitation that I have as a person, right? I don't see a lot of diversity of colors. I have a very, a much more limited, range of colors available to distinguish. So normal vision people can distinguish over 1 million colors, which is amazing, of course. I'm not really sure what the amount will be for me, but it's much less. And
yeah, this is something that I struggle all the time, and we discuss, in some of our last papers with Marcela, with Bruno, with all the guys here in the unit, we are trying to learn how to make better figures and better color scheme for our images. But we struggle to say, okay, this color scheme is able to show what we show in the previous one, right, in the shed. but sometimes we lost things, right? We lost degrees of colors that you cannot have. And this is a difficulty. I don't know. It's a challenge.
Yeah, and I think people say you shouldn't use the rainbow anymore, but if you have, for instance, spectral data that range from 400 to 700, I think there it still should be okay to use this rainbow, because this rainbow is actually representing spectral data.
Spectra, exactly.
So there it should be okay, I guess. And then I think if I look at the spectral range, there is this middle area where you go from green to yellow. And for me, it's quite hard to distinguish green from yellow. So it looks like a big blob of the same color. But again, if you represent the spectra and the exact color may not be that important. So I think, in those cases, it still might be pretty much okay. Yeah.
And then I have another, a big comment that we have learned from your papers, and we have here in our room for microscopy some of the suggestion you have done in your papers about two colors, right? Move from the green and red and use magenta green and some other scheme. And I think most of the people are receiving this very welcome, and it's just an easy things to do. That also the figures look pretty good, and they are beautiful. It's just for a little change. So why not do it? Why it's just something to be helpful for others. But the thing is, something that also is interesting that you mentioned about this superplot and all these opportunities, this kind of a different way of representing our data. It made me think about how valuable this tool per se are, instead of trying to compare things just for a statistical difference, right? Because with this superplot, when you have three replicas of the same experiment comparing A or B, if you use the regular way, you will be averaging 3 points and then another 3 points. But here you are showing all the diversity you have. And when you show all the diversity, of course, the significance is important, right? Do a statistical analysis is important, but the data is telling you why more. That just if something is 0.05 different or not, right?
I'm glad you see it that way. I prefer to look at the data, right? Instead of looking at the p-value. It's because the data gives you so much information. Yeah, and I must say, all the credit for the superplot idea go to this guy I think he's from the UK, Samuel Lord. He came up with this idea. I mean, it's so straightforward, but it's a brilliant way of showing these kind of replicates.
How is your experience in publishing, right? Because the problem is when you go to a journal, they ask you for the significance. They say, this is significant or not. How we can overcome this?
So of course I also got these comments like there's no p-value, what's going on here? So I can also, so one of the things that we do quite often is show the confidence intervals, because the confidence interval is quite directly related to the p-value. And then we say, we provide the confidence intervals, and if they don't overlap, it's a good sign of statistical significance. And then usually referees agree. They say, okay, fine. And another solution that, I mean, if they keep on pushing, okay, I will put the p-values in my graph, fine, right? Or you can also put them in the supplemental to hide them a bit. So that's the way to deal with it. But it's a thing that comes up all the time, because it's also people have to calculate the p-value because everybody does it, and it's not questioned anymore, right? Whether it's very useful or not. It's just a habit, which I find it's pretty
No, absolutely. And the last question that I have is more in the there are in the Fishy there are some of these plugins where you can see if your preparation figure may lack of differences when you have any kind of disability with the color. What is your opinion about them? Did you ever explore? They are good or they are?
It's also very hard for me to judge, but I think the best thing would be if a normal person and a color deficient person sit next to each other.
Okay.
And then explore whether this works, right? I don't know whether it works because I cannot see the difference.
Okay. Okay.
So I think, yeah, how to do that. I think someone with full color vision can, of course, explore with this plugin a data visualization, and then if he sees that, okay, I put this in, and okay, for a color blind person, this becomes very bad. And another one, oh, this one is still okay. And then you can go to the colorblind person and see whether he agrees with this is bad and this is okay. And in that way, you can kind of find out if this simulation works well. But yeah, I don't know. So I think also the problem is then you have to do the simulation for the green colorblind person, simulation for the red colorblind person, and then I think it's better just to keep to stick to colorblind friendly palette, and it should be fine. And you don't have to do simulation. But okay, it's yeah,
absolutely.
Yeah.
Well, I don't know if there is any other question from the audience. I cannot see in the chat any other.
And also, I think, I mean, if you do a little bit of effort, that's already okay, right? I mean, you don't have to be super paranoia, like, oh, this has to be right for everybody, for the whole world, right?
Yeah, no, absolutely.
I have a question. Can you hear me? Yes, I want to know because I was with a problem here and I couldn't hear you when you talk about grayscale and viridis, okay? And what did you say about that? Is it better or more useful to use viridis over grayscale?
Yeah, it's a good question. So personally, for microscopy, single channel microscopy data, I prefer grayscale. Maybe that's a bit conservative, and of course you can apply a color. And I think the main function there of the color is that you start to see other little details. So sometimes the color can be used just to enhance certain details. But yeah, if that's not necessary, you can also always display the single color data as black and white. And you can, of course, play around a bit with that. Yeah.
Right, because I program in Python, and by default you use, Python uses viridis. So sometimes people ask me to use grayscale, and I didn't know why when they program matplotlib, the library, in Python, I don't know why did they choose viridis for that, and maybe it was because it's better or something like that.
Yeah, I think. Yeah, I think it's one of the better color scales. So I think they use that for the default. I think there's this big fuss about MATLAB using Jet as a default color scheme, which is then bad. And so I think they're also moving to other defaults to improve that. Yeah.
Great. Thank you.
Yeah, welcome.
Yeah, I think the other important point that we have learned today is that there is no point to bother in when you are making a merge of 2 or 3 colors to show each of the images independent in color. The recommendation of having grays is great. I mean, what is the point if they are alone to put a color, and then you can put the merge with all the colors. And I think this is something that is something simple and also important for easy, looking for all the people. So, well, I don't see any other questions. So I really wanted to thank you very, very much, Joachim. I hope we can have you in the future in other seminars, more scientific. focus on data of science and your biosensors and FLIM and FRET. And thank you very much again for participating in our seminars.